Next, we are going to see how to represent a relation in a matrix form. If capital R is a relation from the set A equal to A1, A2 up to AM to the set B equal to B1, B2 up to Bn, where the elements of A and B are assumed to be in a specific order, we represent the relation R in a matrix form as Mij equal to 1 if the relation belongs to ai comma bj belongs to R, and 0 if ai comma bj does not belongs to R. There are many types of matrix representation of relations. Matrix representation of R union S is equal to matrix representation of R join matrix representation of S. Matrix representation of R intersection S equal to MR and MS. R inverse is equal to the transpose of the matrix representation of the relation R, where the composition of matrix representation of R and matrix representation of S is nothing but the normal matrix multiplication. Let us explain each and every operation with an example. If capital R and capital S are the two relations on the set A, they are represented by the matrices MR equal to 0, 1, 0, 1, 1, 1, 1, 0, 0. Matrix representation of S equal to 0, 1, 0, 0, 1, 1, 1, 1, 1. If you want to find out the matrix representation of R union S, it is nothing but matrix representation of R join matrix representation of S. Here we will join the corresponding elements 0 or 0, 1 or 1, 0 or 0. A11 of matrix representation of R with A11 of matrix representation of S. Similarly, for the second row also 1 or 0, 1 or 1, 1 or 1. Third row 1 or 1, 0 or 1, 0 or 1. 0 or 0 is like a boolean addition. So 0 or 0 is 0, 1 or 1 is 1, 0 or 0 is 0, 1 or 0 is 1, 1 or 1 is 1, 1 or 1 is 1, 1 or 1 is 1, 0 or 1 is 1, 0 or 1 is 1. In the same way, we can find out the matrix representation of R intersection S. It is nothing but the meet of the two matrix representation. We will find out the meet of the corresponding elements. A11 is 0 here, A11 is also 0 in MS. So we'll find out the meet 0 and 0. 0 and 0 is 0. Similarly, A12 is 1 in matrix representation of R, 1 in the matrix representation of S. 1 and 1 is 1. Similarly, A13 is 0 in matrix representation of R, and A13 is 0 in matrix representation of S, and 0 and 0 is 0. Similarly, for the remaining rows. Therefore, we get matrix representation of R intersection S as 0, 1, 0, 0, 1, 1, 1, 0, 0. Next, we will move on to the composition relation. That is matrix representation of R composition S is matrix representation of R composition matrix representation of S. Here we normal matrix multiplication row into column. Take the first row elements 0, 1, 0 and first column is 0, 0, 1. We multiply by the normal matrix multiplication. 0 and 0 is 0 or 1 and 0 is 0 or 0 and 1 is 0. Similarly, for the remaining rows and columns, we get the matrix representation of R composition as 0, 1, 1, 1, 1, 1, 0, 1, 0. Next, we will move on to the symmetric difference. Matrix representation of R, symmetric difference S is nothing but M R union S minus matrix representation of R intersection S. Here also we will subtract the corresponding elements of the two matrices. 0 minus 0 is 0 and 1 minus 1 is 0, 0 minus 0 is 0. Similarly, for the second row, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 0. For the third row, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 0. Next, we'll find out the matrix representation of R inverse. It is nothing but the transpose of the matrix representation of R. When here the matrix representation of R is 0, 1, 0, 1, 1, 1, 1, double 0. So when you want to find out the transpose of a matrix is nothing but the row becomes a column and column become the rows. So therefore, MR inverse is 0, 1, 0, 1, 1, 0, 0, 1, 0. Lastly, we'll find out the matrix representation of the complement. R complement is nothing but the set of ordered pairs which is not present in the matrix representation of R. 1, comma 1, 1, comma 3, 3, comma 2, and 3, comma 3. Then we will convert the representation relation R complement into matrix form. So we get M R complement equal to 1, 0, 1, 0, 0, 0, 0, 1, 1.